Let's jump up to chapter 9 and take a look at hybridization in the localized and delocalized electron models. Localized is the theory that we kind of stick with. The delocalized model is featured in Zumdahl. It is a very relevant modern theory, but it's not practical for the AP test. So we'll mention brief pieces of it, and that's about it. So we've been drawing Lewis structures to explain bonding, and we've been using the localized model. What that means is electrons we perceive to be belonging to a certain atom. That's the localized electron model. The electrons belong to the atom. And recall with metallic bonding, we learned that the electrons become delocalized and become part of a giant structure. And that's sort of usually kind of a preview of the delocalized model of the atom anyway. But what we're going to do, though, is we have to better explain how and why we get bonds to happen. And single bonding seems pretty straightforward as far as electrons share, but multiple bonding we need to give better explanation for, because when we look at a model of, for example, methane, you have to keep in mind that we're calling all four of these bonds equal in magnitude, energy, and that we have to find a way to explain this given the orbital models we've designed. So we have to do that. How can we get four equal bonds out of an S and P sublevels? We have 2 electrons here and 2 electrons here. How do we get these to bond with equal energies if they're not the same thing? And that's a really important feature of this unit. So again, we're in chapter number 9 now. So if you're looking in the book, take a look there. So this is called sp3 hybridization. S means there's 1 s orbital and 3 p orbitals in sp3. And so if we look at what we consider those to be electrically well defined for us in previous units, we can imagine that instead of viewing them in a molecule as an s and 3 p's, we have 4 sp3 orbitals. In other words, they become, instead of this, these 3 things. There are analogies out there that say, like, you put them in a blender and you get this, which is a little bit silly. The reality is we need to look at these in a little bit more advanced light, which says that when you have different electrical interactions, you get different orbitals, which is a little bit more realistic. So let's take that and run with it. Let's let these 4 orbitals form around carbon, and keep in mind we still have a core orbital there of the 1s subshell, or 1s shell, and this is going to be the second energy level for equal energy orbitals called sp3 orbitals. What happens is, and this is in this example, nitrogen has 2s2, 2p3. What we see happen in those 4 sp3 orbitals is there's a pair here, and then 3 singly occupied orbitals, and so we get the paired orbital here, and then we get 3 singly occupied orbitals here, here, and here. And what those do is form sigma bonds with the hydrogen s orbital. Okay, a sigma bond is a single bond. So what we see here now is sp3 hybridization among ethane, which is C2H6. And we have carbon forming 4 identical sp3 orbitals, bonding singly to 3 hydrogen s subshelled plane orbitals. They aren't hybridized. There's nothing to hybridize with. And then you have 2 of the carbons bonding one another. So this becomes a sigma bond at each one of these points where we see electron overlap. So how do we form a double bond? sp2 hybridization, what we see for carbon again, is we have 2s2, 2p2. We can the old term is promote an electron from the s subshell to the p subshell. It's more of explaining what we're doing. And we have 4 identical orbitals. Well, in sp2 subshells, one of our identical orbitals isn't used, and so we don't hybridize and form 4 identical orbitals. We form 3 identical orbitals, and then we leave one unhybridized orbital, in this case, one of our 2p orbitals. So let's take that idea and run away with it. We have 1s and 3p orbitals, 2 of which are going to hybridize with our s and form 3 identical sp2 orbitals. Remember, s is 1s and 2p orbitals, so there's 3 available for hybridized bonding, and there's 1 that's not hybridized at all. It's just a regular old p orbital. And so in space, what you get is this. You get a trigonal planar shape within this y dimension. We see our unhybridized p orbital. How does it bond? Well, Similar to doing when we did ethane, we can also do ethene, which is C2H4. And what happens here is, just like in ethane, our hybridized orbitals form sigma bonds with hydrogen and then with the carbon across the center. And then we also, in the different plane, in the y plane, we see our p orbitals that were not hybridized. And it takes two carbon nuclei to do this, two atoms to do this. We form two identical p orbitals, and those share a pair of electrons above and below the internuclear space. So here's my sigma bond right here. This is where my hybridized bond orbital is. It's drawn well here. We see that in a different plane, we have two electrons being shared above and below the plane of the internuclear space where the sigma bond is, and that's a pi bond. Now, that's two different p orbitals from two different atoms sharing two electrons total. So in 3 dimensions, we get this structure here with a pi bond and a sigma bond. That's a double bond. You can kind of see now why I call it one electron domain, is it's one area where electrons are being shared between two atoms. It's not just two electrons now, though, it's 4 electrons. And so you might gather that sp hybridization then is still similar. We have one s and one p hybridizing and two p's left unhybridized. Okay, we have 2s2, 2p2 of carbon again. We're dealing with carbon the whole time for consistency's sake. And we see that we can hybridize and form two identical 2p orbitals and then two sp orbitals, and then leave behind two unhybridized 2p orbitals. So how are those going to bond? We see that we got the s and 3p orbitals forming two hybridized sp for sigma bonding and two unhybridized p orbitals that will form different dimensions pi bonds. And so here we go. Our hybridized orbitals form our sigma bond with the other carbon and sigma bond each carbon, or on each hydrogen. Then in two different planes, we have two different pi bonds. We have one in this light blue pi orbital here, or p orbital here, and the p orbital here forming one pi bond, and then the purple forming another pi bond. So a triple bond is what this is. We see we have one sigma bond here, and then a pi here, and a pi here. And the pi bond is this whole expanse, this entire dimension in purple. Just two electrons occupy that big old space. Same thing is true of this light blue. So now you've seen hybridization. This explains hybridization for up to 4 sigma bonds. What it doesn't explain is 5 and 6 sigma bonds like we see when we get expanded octets. We used to use d subshells in hybridization, but data shows that d subshells don't hybridize in the way we were thinking in the past. And so this bit of chemical theory is evolving presently. So you may see in chemical textbooks in the next few years a more thorough, more accurate, consistent with data explanation for how we form sigma bonds with 5 and 6 species around a central atom. But for now, you do not need to know or be able to work with d subshell hybridization. You're not responsible for that. So to recap, sigma bonds are formed when end-to-end overlap of atomic orbitals between two nuclei in the internuclear space. Pi bonds form by side-to-side overlap of unhybridized p orbitals outside the plane of the internuclear space. A single bond is a sigma bond, a double is a sigma and 1 pi, a triple is 1 sigma and 2 pi bonds. And finally, I wanted to get into the molecular orbital model, which explains electrons, instead of being a part of each atom involved in a bond, the electrons are more a function of the entire molecule, which stands to reason. And it's supported by lots of data. It's just that it's rather complex and a little bit beyond the scope of this course, but I want to explain it anyway. In the molecular orbital model, the molecule is assuming a new entity consisting of positively charged nuclei and electrons, and they're going to form an entirely new relationship based on attraction and repulsion. MOs, or molecular orbitals, are constructed from valence electrons and atoms, and you will see, if you go digging, you might find some texts that show core electrons can participate in MOs as well. But keeping it simple, just like atomic orbitals that we're used to, MOs can hold 2 electrons with opposite spins, so those old rules still have root. There are 2 classes of molecular orbitals. There's orbitals that are considered bonding orbitals, and there are anti-bonding orbitals. And it also stands to reason that bonding orbitals are of lower energy than anti-bonding orbitals. So if this is the energy of our original atomic orbitals, our molecular orbitals are going to be of lower energy. And what we know about bonding, this stands to reason. Okay? A bonding orbital is lower in energy than atomic orbitals from which they're composed, and anti-bonding is of greater energy. Okay, greater energy. So these are rather unfavorable. In a bonding orbital, electrons have the greatest probability of being between nuclei. In an antibonding orbital, electrons are mainly outside the internuclear space. You can have S and P molecular orbitals. Orbitals are conserved. In other words, however many you've got in your atomic orbitals, that's how many you're going to have in molecular orbitals. We will discuss bond order only in these simple terms. Bond order is determined as the measure of the stability of a molecule. Using the localized model, the bond order is equal to the number of shared electron pairs between atoms in a bond. So this is the one case where it is significant what type of bond. The bond order of a CC single bond is 1, of a double bond is 2, of a triple bond is 3. And so, for example, triple bond is a bond order of 3. An important comparison here is like in, let's do nitrate. In the nitrate ion, we see we have this structure, and there's a double bond and 2 single bonds. And so we would say the average bond order in a nitrate is 1.33. It's an average of the bond type 1, 1, and 2. So the average would be 1.33. So bond order is essentially the number of shared electron pairs between atoms in a bond. So 1.33 pairs per bond is the average bond order for a nitrate. Finally, our last topic, we're going to talk about magnetism very briefly. Paramagnetism and Diamagnetism are features of electron configuration that predict the behavior of a substance in a magnetic field. Substances that have orbitals with unpaired electrons are weakly attracted to magnetic fields and are paramagnetic. So, for example, if we had, let's just do the valence shell of oxygen. Oxygen is a paramagnetic atom. We have 1s2, 2p4, which we have 2 unpaired electrons. And so oxygen is paramagnetic. They are attracted to the magnetic fields. If you pour liquid oxygen into a magnetic field, the liquid oxygen will stick onto the magnetic poles. Those whose electrons are paired are very weakly repelled by magnetic fields and are called diamagnetic. That would be anything where you have all paired orbitals. So that's fairly straightforward, little brief memorization piece. So keep in mind what that means. That we need to put in contrast with ferromagnetism. Ferromagnetism is much stronger than paramagnetism and is exhibited commonly by metals like iron, cobalt, and nickel. And that concludes this video.